Good question. Boarding school accommodating 400 students has provided a locker to each student. Santa places a pen in every other locker. Every other means alternate lockers. So if Santa placed a pen in 5, the next pen will be placed in locker number 7, so on and so forth. Santa will skip one locker. That's essentially the idea. A box of chocolate in every third locker and a bottle of wine in every fifth locker. What is the starting point? Second locker for a pen, third one for a box of chocolate, and fifth one for a bottle of wine. So the first thing, always do it this way. Don't figure out what kind of a question this is. Just list down the first few things. That gives you an idea about where all Santa placed a pen, where did Santa place a chocolate, so on and so forth. We'll get some idea based on that. And then we can build either the theory to solve this question, or we can list down and finish the question. Let's start with pens. I'm going to put down the locker numbers where pens are placed. Santa starts with a 2. So 2, 4, 6, 8, 10, 12. All these numbers are going to get a pen. Move on to chocolates. In the case of chocolates, starts with a 3. Every third, 3, 6, 9, 12. Before I proceed any further into the wine, we'll just look at this. Any number which is a multiple of 2, here it's quite evident, has got a pen as a gift. Any number that's a multiple of 3 has got a chocolate as a gift. If someone's locker number is a 6, as a multiple of 2, Santa has to place a pen there. And as a multiple of 3, Santa would have given that person a chocolate. So 6 as a multiple of 2 and as a multiple of 3 has got both these gifts. So a number that's a multiple of 2 and 3, a common multiple of 2 and 3 is going to get both these gifts. So 6 has got both these gifts. 12 would have got both these gifts. Our question is to figure out who would have got all 3 gifts. The third gift, which is chocolate wine, is placed starting from the fifth locker, every fifth locker, 5, 10, 15, 20, so on and so forth. Have a look at it. The 10th locker, because it's a multiple of 2 and 5, has got both a pen and a bottle of wine as a gift. Look at the 15th locker, has a multiple of 3 and as a multiple of 5, has got both a chocolate and a wine as a gift. So if any combination is asked, all we have to do is basically pick common multiples to that. We need to find out how many students got all 3 gifts. Before we go to the how many, let's find out who is the first student who would have got all these 3 gifts. The first number to be a multiple of 2, to be a multiple of 3, and that number which is a multiple of 5, a number that's a multiple of 2, 3 and 5. The first such number is the one which would have got all these 3 gifts. Essentially, we are talking about the least common multiple of 2, 3 and 5 is that locker which is the first locker to get all these 3 gifts. Prime factorization method, we would have prime factorized these numbers. 2, 3, 5 are all prime numbers. Therefore, the LCM is going to be equal to 2 into 3 into 5, which is equal to 30. So quite honestly, if you had listed down for a while, you would have figured out that 30 is the first number that comes in all of these 3 lists. Right? So even if you did not figure out the theory, you should have got the answer. Now the 30th locker has got all the 3 gifts. Who would have got all the 3 gifts again after 30? Any multiple of 30 will be a multiple of 2, 3 and 5. So 30, 60, 90, so on and so forth. We need to find out how many students have got all these 3 gifts. So how many lockers are there? 400 lockers. In 400, how many multiples of 30 will be there? Divide 400 by 30 and find out the quotient of this division. 400 by 30 is equal to 13. So 13 lockers or 13 students would have got all the 3 gifts. Right? So it's a pretty straightforward LCM question. We'll just take it to the next step. We'll kind of consolidate whatever we have learned in this step. Whoever got a pen, basically the pens moved in steps of 2. Chocolates moved in steps of 3. And bottle of wine moved in steps of 5. So if it is placed, if these are in intervals of 2, 3 and 5, these are 3 events that repeat with a periodicity of 2, 3 and 5, then all 3 of them will coincide once in x steps. That x steps is going to be the LCM of 2, 3 and 5. We're essentially stating what we stated in the earlier lesson where we talked about when to use LCM. I'm going to take you to an interesting variant of this question. Most of the data in this question is the same. The difference starts here. Santa places a pen in the first locker, not in the second. A box of chocolate in the second one, and a bottle of wine in the third one. That's where he is starting. In the original question, he started with the second one for the pen, third for the pens, for the chocolate, and fifth one for a bottle of wine. So we essentially moved as multiples of 2, multiples of 3, multiples of 5. It became a little easier for us to solve. This is a little trickier. We need to check out how it moves. Let's start with a pen. As usual, let's list it down. That's the easiest one to go with. Started with the first locker for a pen. Third, 5, 7, 9, 11, 13, 15. I'm just going to list down for a while. 17, because the last time we got the first locker to get all the 3 gifts was basically locker number 30. So I'm just going up to 30. We'll see whether it makes sense. 17, 19, 21, 23, 25, 27, 29, 31. If needed, we'll list more. Box of chocolate. Where did he start? Started with the second one. Every third one. So you need to keep adding 3 to it. 2, 5, 8, 11. I'll hold on here. Let's check out who all have got both a pen and a chocolate. 5 has got a pen and 5 has got a chocolate. 11 has also got a pen and 11 has also got a chocolate. So how many steps did we have to move to find the second coincidence? We had to move 6 steps. Just keep this thought in your mind. We'll just proceed with this process. 14, 17, 20, 23, 26, 30, 30. Sorry, I think I made a goof up here. It's not a 20, 30. It's a 29, 32, so on and so forth. Let's move on to plug in that bottle of wine as well. He started with the third one. So next one is going to be 8, 13, 18, 23, 28, 33, 38, so on and so forth. Now that we have listed it down, let's find out the first student who would have got all these 3 gifts. Right? The number that's common to all the 3 sets, 23 is that number which is common to all the 3 sets. So the first step there, we found out who was the first student to get all the 3 gifts. It was rather easy there basically because we had to basically look at multiples of 2, multiples of 3, multiples of 5 and common multiples because it started with a 2, 3 and 5. Here, the numbers are not multiples of 2. The periodicity is a multiple of 2. Numbers are not multiples of 3. Numbers are not multiples of 5. So it became a little more interesting or difficult to figure out the first student to get all the 3 gifts. Is this the only way? This is probably a very good way to find out from the examination perspective. See, there are ways to improve upon this. Let me just point out to you something. The first one is set of odd numbers. The second one is essentially going to be a 3, 8, 13, 18, 23, 28. It's going to have only these 2 numbers. The unit digit is going to be either 3 or the unit digit is going to be 8. The first set basically, we'll just look at pens and wines to start with. The first set had all odd numbers. The third set had 3s and 8s. Then every number that ended in a 3 is going to be a number which is going to be common to both these sets. Now that you have figured this out, all that one has to do is basically list down numbers in the second set and figure out the first point where you encounter a unit digit of 3. That would have given us the answer. So this is basically shortening the step, but I think whatever you have done is good enough from an exam perspective. We have found the first student. The first student to get all 3 gifts is the 23rd. Who's the next one who is going to get it? We'll again use the process before we arrive at any other judgment to how to go about it. Let's just list it down. This is what we have. Put this thing together. So 23 is the first person to get all the 3 gifts. Now, let's figure out who else is the next one who is going to get all the 3 gifts. That's the next process. Just proceed with along this line. Let's check out what happens in this. Right? See, whatever we discovered in that step, I'm going to use it here. Any number common to both these sets is going to end in a 3. So there is going to be 23, 25 and all of those things. I'm going to skip all of that. I'm going to run away straight to 33, 43, 53, 63 in this set. So I save myself the trouble of listing things down. Here I've listed down this 28s and 38s. We can actually not list them down. It's not that they don't get these gifts, but to save steps, it's going to be 23, 33, 43, 53 in this too. Now let's list down for chocolates. For chocolate it's going to be 23, 26, 29. Proceed along the same line. We realize 53 is the next time that the chocolate set hits a unit digit of 3. So 53 is going to be a part of all the 3 sets. So 53rd locker is the second locker to get all these 3 gifts. The first one was 23. The second one was 53. What's the gap between these two? The gap is essentially going to be equal to 30. If you proceed along the same lines, you'll realize the next one to get all the 3 gifts is going to be locker number 83. Because 83 definitely features in both these sets. The gap between these is 3. The 10th step from here is a 30. So 10th step from here will be another 30, which is going to be an 83. Now that we have figured out that every 30th locker, every 30 lockers is when Santa repeats all the 3 gifts, we need to figure out how many students have got all the 3 gifts. One is hand counted, 23, 53, 83, listed down. We are not going too far, it's only up to 400. We'll probably find a better way. This 23, I know we are moving in steps of 30. What is it in relation to a 30? 23 is equal to 1 into 30 minus a 7. 53, let's just check it out. 53 is equal to 2 into 30 minus 7. So any locker who is going to get all the 3 gifts is going to be some multiple of 30 minus 7. Let's just proceed along the way. 13 into 30 I know is essentially a 390 minus 7 is equal to 383. I'll push one step further, which is 14 into 30, 420 minus 7, which is 413. But we have only 400 lockers. 413 cannot be a part of this set. So we started with the first multiple of 30. We went up to the 13th multiple of 30. So how many students have got all the 3 gifts? The answer has not changed. It's still the same 13. It's a much more difficult question than the first one. Consolidate this in the next step. Essentially, these are all the guys who got the gifts. They skip the steps as I mentioned. The important thing is, this moves in steps of 2. The second set moves in steps of 3. The third step moves in steps of 5. Once you have figured out the first one, because this is something you have to iterate it. You go about it trial and error. You either use the shortcut that we derived later on, or you list down the way we did it initially. There is no other alternative. You need to figure this number out. Once you have figured this number out, if they move in steps of 2, 3 and 5, then they're going to move once every time. The coincidence is going to happen. Will be the LCM of the steps in which they move. LCM of 2, 3 and 5, which is equal to 30. I'm reiterating it. The gap between 2 coincidences will be the LCM of 2, 3, 5. But the LCM itself cannot give you the starting point. The starting point is something we need to manually figure it out. Right? Basically, this is what I've said here. Once you have figured out the starting point, every coincidence happens once every x steps. X being the LCM of the individual steps that each of these things take. Give you 2 more interesting questions to ponder with. Is it possible that 2 events that occur with different intervals, let's say something appears once every 3 steps, another thing appears every 5 steps. I'm not saying 3 and 5 are the answers. I'm asking you to figure these 3 and 5 out that do not have a meeting point at all. The last couple of questions that we did, we found a meeting point. 23 was a meeting point. 30 was a meeting point. Is there a possibility that the intervals could be placed in such a way that there will not exist a meeting point? You can assume that there are infinite students. Why I'm stating this is, you could smartly state that Santa places a pen once every 300 steps and starts with the 102nd student. Then obviously there will be no meeting point for a pen and a chocolate. Let's say for a chocolate, it's every 250 steps. And he starts with 142nd student for the first chocolate. That is not what I'm saying. I'm saying these steps should be, they're small enough numbers. It should not be something where you take it out of the range, which is why I've given you infinite students. Right? So there is no way that you can run out of students. Can I pick such intervals where there can exist no meeting point? Think about it. The second variant is again an interesting one. I've kept most of this part of this question the same as the original one that we started. The question I've asked is, how many students have got none of the 3 gifts? Did locker number 1 get any of the gifts in the first one? Obviously, we started with 2. So 1 did not get a gift. Who else did not get a gift? 7 did not get a gift. So proceed along these lines. Figure out a way to count the number of students who have got none of the 3 gifts. Obviously, hand count is not the way. You probably will want to start with a hand count and then evolve a method. We covered quite a bit in this video. It's a lot of concepts to cover in one single video. Time we took a break. Use the break for 2 things. 1, subscribe to this channel. And 2, sign up for the most comprehensive and affordable GMAT Quant course that's available online at gmat.visaco.com.